And I thought I had opened PowerPoint. There it is. We'll go from current slide. And we will get our pin color selected. Okay. Any questions from anything we've covered so far? Any questions? Okay. Now where I have the mark is 4.1.3. This is Chapter 4, Higher Order Differential Equations. 4.1.3, Non-Homogeneous Equations. All right. Now, just a little bit of review here. I know we've had spring break. It's been a long time. Remember, we have two types of homogeneous equations. One kind is that every function is at the same power, basically. You know, if you're raising something, if you got third order differential equation, every term in every order, the x's and y's, the powers add up to the same number. Okay, that's homogeneous in that nature. What we've been talking about so far here are linear equations of a form, trying to find the beginning of it because this is a long subsection, when all of your higher order differential equations are equal to 0. Okay, that would be homogeneous in this first or second sense, however you call it. Now in 4.1.3, we're going to talk about non-homogeneous equations. Now, how this differs from homogeneous, any function y sub p, and when you see that, you think particular solution or particular integral of the equation. Any function y sub p free of arbitrary parameters. Oh, sorry.
What page are we on?
124. Bottom of 124. 4.1.3. And this is supposed to be preliminary theory, and they've sure drug it out really badly. So, any function y of p free of arbitrary parameters. Okay, remember when you're solving your thing and you come up with the arbitrary parameters, those are solutions to your differential equations. This y sub p is free of arbitrary parameters, but satisfies the differential equation, and they go back to number 7. I've got to find it. It's on page 119 under 4.1.2. Number 6 listed the linear nth order differential equation that was homogeneous, and number 7, those that are non-homogeneous. The only difference is everything on the left-hand side of the equation is the same. Your coefficient functions, your derivatives, nth degree derivative, all the way down to the function itself, but homogeneous is going to be equal to 0, non-homogeneous is going to be equal to some function of your independent variable, in this case x. Okay? Now, for example, let's see, it is a straightforward task to show that the constant function y sub p is equal to 3. No parameters in that. No arbitrary constants. Okay? But that is a function, that's a straight line function. Always 3. No matter where the x value is, the y is always 3. Okay? Pretty simple one. It's a particular solution to the non-homogeneous equation y double prime plus 9y is equal to 27. Okay? Well, if y is equal to 3, y sub p is equal to 3, y prime is 0, y double prime is 0, right? Because of the constant. 9 times 3 is 27. There's no constants involved, nothing else. That's just a particular solution that's always going to work with us. Sure, there's going to be lots more equations that will work, but that's a particular solution that will always work irregardless of constants. Okay? Now, let's say we have a bunch of other solutions. y1, y2, y3, ... up to y sub k, I believe is the counter they use for this one, yeah. That these are solutions for that homogeneous form on an interval I, and that y sub p is in one of these other particular solutions of solution 7. That's the non-homogeneous case, okay? Just like this one right here. That's non-homogeneous. It's not 0, okay? Then the linear combination of these, y is equal to c1y1 of x plus c2y2 of x plus c3y3 of x plus ... plus yp, and that could be of x or not. It could just be a constant. That is also a solution. Okay, I probably should have included the plus c sub k yk of x. All those, these were all solutions to whatever your new differential equation is. Okay, and yp is a particular solution. These can have the arbitrary constants all the way up. Every one of those has its own arbitrary constant. Sum of those together is a solution, but also the sum of those plus your yp. It could be a function of x as well, that particular solution. Okay? That's also a solution for the non-homogeneous equation. Okay? If you think about it, it makes sense because the linear combinations, this part, all that part, okay, lost my place here, because all that part is transformed into 0 with the operator that we were using before, whereas yp is transformed into g sub x. So if we use k equal n, why they change it, I don't know, linearly independent solutions of the nth order equation 6, then the expression here that has a particular solution becomes the general solution of your non-homogeneous. Okay? So basically, these are the solutions for the homogeneous, and they have with them these arbitrary coefficients. And if this is a solution for the g of x part, the non-homogeneous part, then all these together, that add to be 0, plus this one, which is a solution for the non-homogeneous part, all those added together will form your general solution. So this is called the general solution. It has the solutions for your homogeneous part plus any particular solution for the non-homogeneous part. Okay. So here's theorem 4.1.6, which I think restates what we've just been harping about. So let's erase all this. Let y sub p be a particular solution. Okay, now, you probably won't notice, but if my writing is a little stranger than normal, I got some splinters over the week because I was working with some stuff that we were burning that had briars in it, and some of them made their way through my gloves into my fingers, and I couldn't get them out. And just today, I finally got the worst one out, but it's right on my index finger of my left hand, and it hurts to write, hurts to do just about anything. So if it looks a little strange, that's part of it. Let y be a particular solution of the homogeneous linear differential equation okay. I probably should have put, let me get it all in there. Because these are all important words here. Non-homogeneous linear nth order differential equation. Okay? And that's non-homogeneous, so that was our equation 7 from way back. On some interval I, okay? And let, just like we did before, y1, y sub 2, y sub 3, comma, dot, 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 comma, y sub n, because we know we have n solutions, be a fundamental set of solutions Now, a little bit of reminder, remember the fundamental set, these would be all linearly independent of each other. And there's not just a unique fundamental set, there could be many of them, but this is a fundamental set, linearly independent of each other. Set of solutions of the associated homogeneous differential equation, okay? That was number 6, remember, on that same interval I. Then, that's the given. Then the general solution will be a linear combination of those. Y is equal to C1, Y1 of X plus C2, Y2 of X. All those in the fundamental set plus C3, Y3 of X plus dot, 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 all the way up to and including Cn, Y sub n of X, plus then your particular solution, Yp, which could be of X also, okay? They usually don't put the X there, but generally it is, okay? Where the Ci's are arbitrary constants. These are arbitrary constants, okay? And you have a whole family of curves there. Usually if you have enough boundary values or initial values or other things, you can identify most, if not all of those. Okay. Now they have a little proof there. I'll let you look at it. It uses the operators and go on. Now, another little definition here. We see in this theorem that we just put here that the general solution of a non-homogeneous linear equation consists of the sum of two functions. Okay, one is your linear combination, which is the general solution of your homogeneous function, differential equation. It's also called the complementary function for equation 7. So this part here was called the general solution for the homogeneous part, but now it's called the complementary solution for the non-homogeneous part, because when you add the complementary with the particular, you get the general solution here. So if it was a homogeneous equation, you stop right there, and that's your general solution. If it's a non-homogeneous, that same place you got to there is called the complementary solution, plus a particular solution now forms your general solution for the non-homogeneous part. All right? Lots of words, okay? And they sometimes get repeated, and just don't get them too confused. So, remember this, the general solution for a non-homogeneous linear nth order differential equation is comprised of a YC, the complementary part, which is the solution for the associated not homogeneous part, plus YP, which is the particular solution for the non-homogeneous part. Okay? So let's look at example 10. Let's clear the slide and do example 10. Here's what they say, and again, they're not telling you how they got it. To me, this seems almost backwards. But here's a y sub p, and they're telling you this is going to be a particular solution, is equal to minus 11/12 minus 1/2 x. Okay? That's a particular solution. It says by substitution, this particular solution is readily shown to be a particular solution, okay, of the non-homogeneous equation y triple prime minus 6y double prime plus 11 y prime minus 6 y is equal to 3x. Okay? Now, what we ought to do is verify what they said is true. Okay? If this is your particular solution, what is yp prime? Pretty easy. Negative 1/2, period. What's yp double prime? And yp triple prime? 0. Okay. So let's plug in what we've got so far. That would be 0 minus 6 times 0 plus 11 times y prime was a negative 1/2 minus 6 times y, which is negative 11/12 minus 1/2 x. Is that equal to 3x? Okay? 11 times minus 1/2 would be minus 11 halves, right? Minus 6 times a minus 11/12 would be plus, 6 will go into 12 twice, 11 halves, right? Minus 6 times minus 1/2, now this will be a 3. I'm canceling things several different ways here. So that would be a plus 3x, sure enough, is equal to 3x, right? Because these two add to 0. So sure enough, that shows that is a particular solution that works for that linear third order differential, non-homogeneous differential equation. All right. Now, that only gives you a particular solution. How do you get your complementary solution? How? Earth to class, come in, please. How do you get your complementary solution? You lose the non-homogeneous part, and you just do y triple prime minus 6y double prime plus 11y prime minus 6y is equal to 0. And you try to come up with a complementary solution for that. In other words, what y will work there. Okay? Now, they point you back to example 9. This is example 10. So you turn back a few pages, well, one page to example 9. Okay? And there they say, here is a solution. They called it a general solution for the homogeneous differential equation. that now becomes your complementary solution for the non-homogeneous one, okay? And that these three functions added together with coefficients, arbitrary coefficients, that will be now your complementary solution, okay? So rather than go back and prove those or anything again, we do this. Y, now it's YC. In the homogeneous part, this would be general solution, Y. For this one, that started off with a non-homogeneous part, we extract this, and your complementary solution will be C1, and if you go back there, that was e to the x plus C2 e to the 2x, right? Yep. Plus C3 e to the 3x. Okay? That will be your complementary solution. Okay? Now, you can do the same thing we did before. You don't have to, because we've already shown this is true, but you can take those derivatives if you want to. The first, the second, and the third derivative. Put them all together, and you'll find out that does come out correctly. So your general solution now, y, is equal to the complementary solution, c1 e to the x plus c2 e to the 2x plus c3 e to the 3x plus your particular solution, which actually is a minus now, minus 11/12 minus 1/2 x. There's your general solution for the non-homogeneous case. Back when we were dealing with homogeneous, if this was a 0, this would be your general solution. With it having a g of x over there, not 0, then the same thing that was your general solution for the homogeneous case becomes your complementary solution for the non-homogeneous case, and then they had already picked out a particular solution that worked, and you plug that in, add that to your general solution, the complementary solution, and now you've got your general solution. Blah, 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 right? Okay. So hopefully that's exactly what they have here. C1 e to the x plus C2 e to the 2x plus C3 e to the 3x minus 11/12 minus 1/2 x. That is your general solution. So here we have another superposition principle, and this is theorem 4.1.7. What if you have more than one particular solution? They just have shown us this happens to be a particular solution. What if you have more than one? So what we're going to do is let yp1, yp2, yp sub 3, comma, dot, 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 comma, y sub p sub, they're using k now, be k particular solutions of the non-homogeneous linear nth order differential equation that we had, non-homogeneous, that was our number 7, on some interval I, corresponding in turn to k distinct functions, g1 of x, g2 of x, these correspond to g1, g2, g3, dot, 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 up to g sub k. Okay? Distinct functions, that is, suppose y sub pi denotes a particular solution of the corresponding differential equation, and it would be just like equation 7, only you have a g1 of, or gi of x here, okay? A sub n of x times y to the nth derivative of y plus a n minus 1 of x to the n minus first derivative 1, and so on and so on. But notice these do not have arbitrary coefficients. Your particular solution, y sub p, would then be the sum of these. Y sub p1 plus y sub p2 plus y sub p3 plus ... all the way up to and including y sub p sub n. Okay, oh, I'm sorry, k. Okay, because you had kg's at the end of your thing added together, then these would be your, this would be your particular solution. Okay. That's the superposition principle. All right. Let's do an example for what it's worth. And again, they're not telling us how they got it. The rest of the chapter is going to do that. Why don't they start out and tell us that? But says you should verify that y sub p sub 1 is equal to minus 4x squared is a particular solution of y double prime minus y, or 3y prime plus 4y is equal to minus 16x squared plus 24x minus 8. Okay. Yuck. All last week, sorry, just a little bit of a break here. We worked at 3 different houses doing spring type work, planting things and weeding things and mulching things and mowing and taking care of things. 3 different yards over the week, and right now I'm so sore I can hardly stand it. I'm just so stiff and sore from being working more than it was fun. I really enjoy it, but goodness gracious, I'm stiff and sore. So what we're going to do y sub p1 prime. What would that be? Minus 8x. How about y p1 double prime? Minus 8. So let's plug these in and see what we get. Y double prime is minus 8 minus 3 times y prime, which would be minus 8x, plus 4 times y, that's yp1, and here's Nigel. He promised he would be back late, and he made it. Good. We're on example 11, bottom of page 126. This is, and here's, I think it's too soon, right? Yeah. I haven't seen him yet. Yeah. He sometimes comes around the back, so if you want to sit in 257, he usually comes in that way to keep from interrupting the class. Yeah, if you need to wait for him. Okay. Minus 4 times, or plus 4 times negative 4x squared. Is that equal to minus 16? Goodness gracious, did I ever write that funky? Minus 16x squared, not 16 squared x. Duh. And y'all didn't catch it. Huh? What are you doing? Okay. Did I get the rest of it right? I think so. Minus 16x squared plus 24x minus 8. Let's see if indeed that's true. Well, I can tell minus 8 is the same as minus 8, so that's correct. This would be plus 24x. There's a plus 24x. That's correct. And this is a minus 16x squared minus 16x squared. Sure enough, that one works. Okay? Now, they also tell us that y sub p2 equal e to the 2x is a particular solution to very same thing, y double prime minus 3y prime plus 4y equal to 2e to the 2x. Okay? Well, how are we going to verify that? Take some derivatives. It would be y prime double p2. E to the 2x. And what's y double prime of p2? 4e to the 2x. So this will be 4e to the 2x minus 3 times 2e to the 2x plus 4 times e to the 2x. Is that equal to 2e to the 2x? Well, let's see. That's obviously 4e to the 2x minus 6e to the 2x plus 4e to the 2x. And that would be 8e to the 2x minus 6e to the 2x. Sure enough is 2e to the 2x. So yeah, there's a general solution, a particular solution to that g of x, non-homogeneous. Well, they also have another one, surprise, surprise. yp3 is equal to xe to the x. And this, they claim, is a particular solution for y double prime minus 3y prime plus 4y. Same homogeneous part, but the g part is 2x e to the x minus e to the x. I don't know. Yeah. My pen gets slowed down for some reason. I guess I got too much on the screen. Well, guess what we got to do? Take some derivatives. I'm running out of room down here. What's your y prime for P3? Okay, starts off being e to the x plus product rule. X e to the x. Very good. Now let's do y double prime of P3. E to the x plus e to the x, x e to the x. Right. I got lost there. Plus x e to the x. Okay, I thought I had already done that. Let me see if I can clean that up just a little bit. Okay, too much. Okay, which, by the way, would be 2e to the x plus x e to the x. Which you could also write as 2 plus x times e to the x. I don't know if that makes it any better. And what's our y? Is that all we need? Yeah, I think it is. Yeah. So let's put all of those together. Your y double prime of that particular solution there would be 2e to the x plus x e to the x, right? minus 3 times y prime, which would be e to the x plus x e to the x. Plus 4 times your y, and your y is x e to the x. And the question is that equal to 2, goodness gracious, no room at the end, 2x e to the x minus e to the x. All right. Whew. All right. Well, here's a 2e to the x plus x e to the x minus 3e to the x minus 3x e to the x plus 4x e to the x. Is that equal to 2x e to the x minus e to the x? That's the question. Here's our answer. There's 4 plus 2 would be 6 ex. Oops. Sorry about that. Let's start over. There's a x e to the x minus 3x e to the x plus 4. So x e to the x plus 4 would be 5x e to the x minus 3 would be 2x e to the x. That part's okay. And here we have a 2e to the x minus 3e to the x would be a minus e to the x minus another one. Woo. Oh, just that's our minus e to the x. These two add to minus e to the x. So sure enough, that does work. All right, so we have one particular solution for one general non-homogeneous part. This part, we have another particular solution that works for this general non-homogeneous part. We have yet another one that works for that non-homogeneous part. Well, what if our linear second order non-homogeneous differential equation was this thing, y double prime minus 3y prime plus 4y is equal to this plus this plus this, okay? Then our particular solution would be this particular solution plus this particular solution plus that. Okay, again, superposition. If you have one that works and you got a multitude of things there, then add them all together, covering every one of them, and you get it. Okay? Here's a little note. If the particular solution y sub p are particular solutions for 12, which is that general case over there across the page, for I equal 1 to k, then the linear combination y sub p is equal to c1 y sub p1 plus c2 y sub p2 plus ... up to ck y sub k, y sub p sub k. Okay, I think the verbiage got a little mixed up there. Let's go back and say, if your particular solution y sub p are particular solutions for any old g sub I of x, and there could be many of them, for I equal 1 to k, then the linear combination of those y sub p sub k's, or i's, of c1 y sub p1 plus c2 y sub p2 plus all the way up to ck y sub pk, where c, i's are constants, that's also a particular solution of the linear nth order I guess general non-homogeneous differential equation. Then you have these. Now it says before we actually start solving homogeneous and non-homogeneous linear differential equations, we need one additional bit of theory, which is presented in the next section, which we're going to get to in a minute. Now, the remark section here, when I first started teaching this, I tried to go over these. This is basically more nomenclature, specific verbiage that, yeah, if you are deep into doing some of this, you might use some of these terms, like linear systems, state variables, state of the system, input function, forcing function, excitation function. But right now where we sit, we aren't there, okay? So I'm going to leave off those things for now. If you're interested in how to apply this, and you may run into some of that verbiage, go back to these sections and it'll probably clear it up for you. So, exercise set 4.1. And the answers to selected odd number problems begin on back in the answer thing. I've already assigned most of these before, either 1 or 3 or both. Any of the odds 5 or 7 or both. Do number 9, do number 11, and do number 13. That was 4.1.1. Finished that a while back. 4.1.2, any of the odds 15 to 21, any of the odds 23 to 29. That was assigned those last time. And 4.1.3, non-homogeneous equations, either 31 or 33, or both if you choose, and 35. Do 35. There are some discussion problems. If you want to dig a little deeper and go for them, help yourself, okay? But if not, no. Section 4.2. This is that last little bit of theory they say we need, okay, before we can start solving homogeneous or non-homogeneous linear differential equation. One additional bit of theory, okay, and that's reduction of order, okay. As if you thought we didn't have enough disorder now, we're going to reduce it even more and have more. So what do we mean by this? Reduction of order. Suppose that, excuse me. Now, I wanted to back off here a little bit. If you remember, back when we started talking about particular solutions, we said they were without arbitrary coefficients, right? But that very last thing we did when we had multiple general, g of x's at the end that made it a non-homogeneous part, and then you had multiple particular solutions that did that, notice they went back and introduced arbitrary coefficients again, which they had said they weren't going to do, but they have. Okay? That's part of your superposition. Okay? And yeah, they do show up again. Let's see if the reduction of order can reduce any order. Okay, let's see what's happening. Suppose that y sub 1 denotes a non-trivial solution of this differential equation. A sub 2 of x, y double prime, plus a sub 1 of x, y prime plus a sub 0 of x y is equal to 0. Give me some features of that differential equation. It's a homogeneous. Second, linear. What order? Second order differential equation. Okay. Doesn't really matter what order what arrangement you make of that. Just make sure you get in those. Homogeneous because it's equal to 0. Linear because your derivatives and the function itself are not, you don't have any multiplied by each other or squared or cubed or anything. And the order is second because that's the maximum derivative you have. Okay, so let's suppose that y1 is a non-trivial solution. Now what is your trivial solution? Works every time on a homogeneous system. Y is equal to 0. Because if y is equal to 0, y prime is equal to 0, and y double prime is equal to 0, as many as you got. And when you multiply whatever a sub x is that you got here times 0 plus this, a1 of x times 0 plus a0 of x times 0, you're going to get 0. That's the trivial solution. We're not talking about this. This a1 is a non-trivial solution. Okay. y1. Okay. And y1 is defined on the interval I. So I'm just going to put on I. Okay. Some interval I. We seek a second solution, y2. Okay. So that the set consisting of y1 and y2 is linearly independent on I. Okay. Such that the set of y1, y2 linearly independent. Okay, making this a term oh man, fundamental set, a fundamental set. Okay. Recall from 4.1, which is that long section we just did, that if y1 and y2 are linearly independent, then their quotient, y2 over y1, or their ratio, I like to think of that as, is non-constant on I. Okay, in other words, you don't have it to the same power or anything else that when you divide it out, it becomes a constant. On I, that is that y2 of x over y1 of x is some function of x, not a constant. Or y2 of x, so let's get all this down there. y2 of x over y1 of x, it doesn't matter which one you put on top, is some u of x where u is not a constant function. Okay? Now if that's the case, that means that y2 of x is equal to y1 of x times u of x, okay, where u is not a constant, okay? They wrote the u first, it doesn't matter. The function u of x can be found by substituting this thing right here into the given differential equation. That method is called reduction of order because we must solve a linear first order differential equation to find u. Okay, so here's example 1. I think I may need all the space, so keep that in mind. Let's hit it. Okay. Given that y1 is equal to e to the x, we've seen that before, that is a solution of y double prime minus y is equal to 0. Tell me something about that one. Describe that equation. A homogeneous, you got that one? Second order. What again? Linear. Linear differential equation. What else were you saying? Say again. Oh yeah, and it's not a trivial solution. Okay, non-trivial solution. Okay, got it. Good. Okay. Well, they say that. They say it's given, and they say on the interval. Okay. Let's just check and see if they're telling us the truth. What's y1 prime? E to the x. What's y1 double prime? E to the x. Y'all are good. Okay. So what is y double prime minus y? 0. Yes. So that is a solution, and it's a non-trivial solution. Very good. Okay. It says use the reduction of order to find a second solution, y2. What we just said, y2 of x needs to be some u of x, not a constant, some function of x times y1 of x. Okay? And it also has to be a solution to this. Bless you. Again. Okay. So if there is that, let's do y2 prime of x. What would that be? Ooh boy, this doesn't look good, does it? A little louder. I can see your mouth moving. I can hear a little bit, but I can't quite put it out. Say this again. Yeah, no, it's u of x, a function, times y1 of x, which is this function. So instead of y1 of x, let's put e of x, e to the x. U of x is some other function. We just don't know what it is yet. Say again? Yeah, okay, that'll be the first part. U of x times e to the x plus product rule. E to the x u prime of x. Very good. Okay. One more. y2 double prime of x is going to be u of x times e to the x. Is that what you said? Right? Plus e to the x u prime of x. That's taking derivative of this, which is exactly the same as that. Plus, you got two more parts here. What would that be? A little louder. Another e to the x times u double prime of x, okay, plus, that was the first time derivative of the second, u prime x, e to the x. Okay. Now, notice here, every term has an e to the x in it. So let's shorten this a little bit and say that's e to the x times, here we have a u of x, here we have 2u plus 2u prime of x plus u double prime of x. Would you buy that? Yay or nay? Okay. The wind bought it too. Okay. Now, the e to the x was this part. Okay? And we already know that works on that. So basically, what we have here is that u double prime of x plus 2u prime of x plus u of x minus u of x, that's from the y part, okay, is equal to 0. Well, u of x minus u of x is 0. So now we have u double prime of x plus 2u prime of x is equal to 0. Okay? Now, I think you'll see that's exactly what they have here. They kept the e to the x in it. I had already gotten rid of it. They kept it in, so I'll put it back there. That's equal to 0. And we know that e to the x can't be equal to 0, right? It never is. So that's why I've already taken it out. So then we have just that this part has to be equal to 0. Okay? Has to be. All right. So we're required, and this is why I had it down there in the first place, u double prime of x plus 2u prime of x is equal to 0. Okay? Now, if we make the substitution w is equal to u prime, oh yay, okay, so w is equal to u prime, then w prime would be u double prime. So then we would have w prime of x plus 2w of x is equal to 0. All right? That looks a lot better, doesn't it? Not really. Okay, but they did. Fine. Which is a linear first order equation in w. And then we can use an integrating factor. Do you remember how we did that? Okay. That is a dw dx plus 2 w of x equals 0. That is what they call a linear equation. And what we're going to do is an integrating factor. Remember this? We sorry. All right. This is the, what do we call it? Row. Okay, who was it? Rodney looking for Dr. Bryant. I don't know if he called him. Did he go next door? Do you know? Okay. Anyway. All right. You go back in chapter 2. 2.3. Your integrating factor, yeah, that's what we called it. That 2 was what we're calling our P of x. Right? What do we do with that P of x? Okay? we integrated the p of x, so integral of 2 dx would be what? 2x, right? What did we do with it? We did e to the 2, so this would be e to the 2x. That's our integrating factor, e to the 2x. Notice that's different from e to the x. Okay. So what did we do with it? We plugged that in here. Excuse me. We multiplied everything on both sides with that. So we had e to the 2x w prime of x plus 2e to the 2x w of x equals 0. Multiply that integrating factor, which is e to the 2x in this case, by everything. Now, what that did for us was we noticed this was a perfect derivative. D by dx of e to the 2x w of x, right? Okay, now, let's make sure that's right. You take the derivative of this, product rule, e to the 2x times w prime, right, plus 2e to the 2x times w, right, okay? Well, if that's equal to 0, that means the thing that's in here must be a constant, right? Or separation of variables, however you want to call that. So that would give you e to the 2x w of x is equal to some constant. What was our favorite? Okay. Let's do this. All right, I'm trying to recall how they came up with plus or minus. Oh, okay, got it. That's equal to some constant, k. Oh, no, that's just equal to 0. No, some constant, okay. So that means our w of x is equal to some constant over e to the 2x, which is some constant times e to the minus 2x. So there's our solution, okay. Okay. Now they call that C1 rather than C. So we'll put a 1 there. It's going to come in important later. So that's our W of x, is this. But remember what W of x was. W is equal to u prime. So this means that du dx is equal to c1 e to the minus 2x. Okay? So let's separate those. I'm running out of room rapidly. Du is equal to c1 e to the minus 2x dx, right? That would put u as being what? Antiderivative. C1's out front. What's the antiderivative of e to the minus 2x? Minus 2 e to the minus 2x. Okay? I think we put a plus C2 in here. Yeah. Because it's not a definite integral, it's an indefinite integral, so you need another constant. Okay. Now I think what you'll find that we have here, u is equal to, oh wait, it's not, it's 1 over 2, right? Integrating, you have to have, if you take a derivative of this, you're going to get back to that, right? And because this is going to give you a minus 2, you'll need a minus 1 half to do that. So it's over 2, not times 2. If you're taking a derivative, it'd be a minus 2c. Integrating is minus 1 half e to the 2. Okay. Now, that's what your u is. So now we have this new function u, and it's not a constant. It has an e term in it with an e to the minus 2x, and then it does have a constant with it, but it's not a constant itself. Okay. Now, I'm rapidly, completely running out of room now, and it's getting so disjointed here. Let me get rid of some stuff. How are we doing on time? We got a couple of minutes, is all right. Yuck. All right, I think we can definitely forego these two, because we've already shown that. Okay. And I think we can probably do without this one. I sure hope so, because I'm erasing it. Okay. Which I think then also enables me to get rid of this one. I hope I can. Hope I'm not doing too much here. All right. Okay. Okay. I think we're okay now. So, our y1 was e to the x. Okay? Our y2 is equal to u, which is this, minus c1 over 2 e to the minus 2x plus c2. Okay? And that's multiplied That's the u of x from here times e to the x from here. Okay? And just to keep it from being confusing, I'll drop this back down on the level it's supposed to be. Yo! This thing falls on me. Okay, let me see if I can pin that a little bit better. There we go. All right. So what do we have now? This y2 is equal to, goodness gracious, my eye hurts. All right, let's multiply these across, and this gives you minus c1 over 2 e to the minus 2x times e to the x would be e to the minus x plus c2 e to the x. There's our second solution, okay? Now, our first solution, you remember, already had an e to the x in it. So we really don't need the second e to the x, so we're going to let this c2 be 0. Because you see, we already had an e to the x here. We don't need another term with e to the x. So we'll just let that c2 be 0. Lucky us, yeah. And the c1, why not let it be a negative 2? Okay? They don't give any reason for it, but let's let it be a negative 2. Basically, get rid of the denominator. So our y2 could be e to the 2 minus, here it is, c1 is equal to negative 2. So that would be e to the minus x, yeah, e to the minus x. Okay? So that gives us that. Now we do the Wronskian, and I think we're out of time. I'll let you finish reading that. It carries on from here. But we'll pick up next time with what they call the general case here. Okay? Sorry we didn't quite have time to finish, but I know Dr. Bryant needs to get in here. So homework exercises here. I think you can do any of the odds 1 through 15. Try them anyway. Okay? And then, that's the homogeneous case. Then we'll throw in something with non-homogeneous later. And we almost finished 4.2. Hopefully we will finish this next time. And then we'll move on to 4.3. And we're actually get to solving some problems now. Okay. So, we'll cover that. Let's go on and delete